This is the fifth part of mathematical physics. In this video we do another special function. First is Legendre equation and Legendre polynomial. This is a Legendre equation. Here n is parameter real numbers. Using power series method, we find the solution of this differential equation. This y is equal to a naught into x raised to power minus n minus 1 plus n plus 1 into n plus 2 x raised to power minus n minus 3 divided by 2 into 2n plus 3 plus n plus 1 n plus 3 n plus 4 x raised to power n minus 5 plus up to so on. This is y1 and their solution is called Legendre polynomial Pn. It is denoted by Pn of x, which is equal to this. Here, when n is even, it contains 1 by n plus 1, 1 by 2 n plus 1 term, the last term being this. If n is odd, it contains one by 2 into n plus 1 terms, and the last term become this. Here Pn is called first kind of Legendre function. Now another solution is a Legendre function of second kind and denoted by Qnx. Second kind, and this is first kind. Here Qnx equal to factorial n divided by this up to so on. Here you can see Qn is non-terminating series. Now Rodrigues formula Pnx is equal to 2 raised to 1 by 2 raised to power n into factorial n dn over dxn x square minus n. This is very important because maybe is a possibility in this time in a TFR this type of question will come. Now legendre polynomials. At a fixed value of x and varying value of n from n equal to 0 to infinity, we can write for n equal to 0 we get p not x equal to 1, and for n equal to 1 we get this value. We put the value of n in this Rodrigues formula and we get legendre polynomial. Now putting n equal to 3 we get p3x equal to 1 by 2 3x square minus 1, and p4x is equal to 1 by 8 35x raised to power 4 minus 30x square plus 3, and for Pnx we get this formula. Now let's plot these value on a graph. This is P1 and this is P naught. Now for P2 this is P2 and P3 x equal to 1 by 2 5x cube minus 3x. This is for P4 and this is 0.5 and this is minus 0.5. And this is P3 and this is P2. This is important relation in legendre polynomial. Now generating function. is equal 1 minus 2xz plus z square whole power minus 1 by 2 is equal to summation n is equal to 0 to infinity pnx z raised to power n. Some important relations. Pn minus x is equal to minus 1 raised to power n. Pnx or Pn minus 1 is equal to minus 1 raised to power n. P dash n minus 1 is minus x is equal to n into n plus 1 divided by 2, and P dash n minus 1 is equal to minus 1 raised to power n into n plus n into n plus 1 divided by 2. And now P2n 0 is equal to minus 1 raised to power n 1 into 3 into 5 up to so 2n minus 1, and divide by 2 into 4 into 6 up to 2n. Now this is another important relation. P2n plus 1 is equal to 0, and similarly for hermite function s2n plus 1 is equal to 0. This is also important for TIFR examination and JEST examination also. Now, important property of legendre function is orthogonal property. Integral minus 1 to plus 1 pmx into pnx dx is equal to this is chronicle delta. It will be 1 only for when m equal to n, otherwise 0. Now another important relation, recurrence relation. This is the first recurrence relation, and this is second. npnx is equal to x p dash nx minus pn minus 1 dash x, and this is another relation. There are total 6 relations in legendre polynomial. Why these relations are important? Because we can convert this relation into many forms. We can put here n equal to n minus 1, n minus 2 to convert these recurrence relation into another form. That's why these are so important and help to solve various differential equation which are in the form of legendre polynomial. Now another important relation, this integral x pn p dash n dx equal to 2n divided by 2n plus 1. Now associated legendre polynomial. This is the differential equation of associated legendre polynomial. Here the universal solution of this equation is here m is greater than n. Now some important property of associated legendre polynomial. Here this is a chronicle delta for only if p and q be same, that's equal to 1. If no, the whole term becomes 0. Now this is a second important relation. Now another topic is Bessel differential equation. X square y double dash plus x y dash plus x square minus n square into y equal to 0. Using Fourier's method of power series, we can solve this Bessel differential equation, and their solution becomes y is equal to a naught x raised to power n 1 minus x square divided by 2 into 2 n plus 1 plus x raised to power 4 divided by 2 into 4 into 2 square n plus 1 n plus 2 up to minus 1 raised to power r into x raised to power 2r divided by 2r r factorial into n plus 1 to n plus 2 up to n plus r. This is the solution of Bessel differential equation. Here a naught is equal to 1 by 2 raised to power n factorial or gamma n plus 1. Here Jnx is the bessel function, and gnx is equal to summation r is equal to 0 to infinity minus 1 raised to power r divided by factorial r divided by gamma n plus r plus 1 into x by 2 whole power n plus 2r. Here we can write, instead of this, using the property of gamma function. Here for n equal to 0, gnx become j not x equal to 1 minus x square divided by 2 square plus x raised to power 4 divided by this up to so on. For n equal to 1, j1x equal to this up to so on. Here j naught x is like a damped cosine function and j1x became damped sine function for large x. Here this graph shows that now recurrence formula for Bessel function. This is the first function or recurrence formula for Bessel function, and we can find this using this formula. Using this formula, first we differentiate this formula and then multiply by x and solve that condition, and we got this recurrence formula. Now another recurrence formula, this. We can get this formula similarly using this. Now this is third recurrence relation. We get using these two equations, first and second, by adding both, and similarly we get this fourth relation by subtracting first and second relation. Now this is important relation. If we differentiate x raised to power minus n jn, we get minus x raised to power minus n jn minus 1x. And if we differentiate x raised to power plus n jnx, we get x raised to power n jn minus x. Now important property, orthogonality of Bessel function. Limit 0 to 1 integral x jn alpha x jn beta x dx equal to 0. Here alpha and beta are the roots of jnx. Now generating function for Bessel function Bessel polynomial jnx, that is this summation z raised to power n jnx, and summation is from minus infinity to plus infinity. Here as we write here the value of j naught x, this is very important because using this various tricky question and easy question will be made. Now trigonometric expansion involving Bessel function. If we put in this equation z equals to e raised to power I iota theta, then we get here this value. Here j minus n is equal to minus 1 raised to power n jn. This is very important formula. Using this formula and using the property of exponential, we can write here this and equal to j naught plus j1 e raised to power iota minus e raised to power minus iota theta plus j2 e raised to power 2 iota theta plus now we use here cos x is equal to e raised to power iota x, cos theta is equal to and similarly for sin theta using this value in this relation we get cos x sin theta equals to j naught plus 2j2 cos 2 theta plus 2j4 cos 4 theta Sorry for that. Now up to so on. Here we get this term because we comparing both side, real term and imaginary term. On comparing real term we get this value, and on comparing imaginary value we get this value. Up to so on. If we put here theta is equal to pi by 2, we get cos x is equal to j0 minus 2j2 plus 2j4 up to so on. Sin x is equal to 2j1 plus 2j3 plus 2j5 up to so on. Now another important topic is bessel integral. Here jn is equal to gnx is equal to 1 by pi integral 0 to pi cos n theta minus x sin theta d theta, and if we put here n equal to 0 we get this another integral. Now this is an important relation. J minus half is equal to 1 root 2 by pi x cos x. Now another important topic is hermite differential equation and hermite polynomial. This is a second order differential equation of hermite differential equation. Y double dash minus 2xy dash plus 2ny equals to 0. Using Rodriguez method, we find the complete solution of this method. Here this is the complete solution of hermite function, hermite differential equation. Here a and b are arbitrary constant. Now this is very important, generating function. This is e raised to power 2x t minus t square equal to summation h n x t raised to power n divided by factorial n, and summation is from n equal to 0 to infinity. Here h n x is equal to minus 1 raised to power n into d n over d x n e raised to power minus x square. This is Rodriguez formula of hermite polynomial. Using this we can calculate various value of h for varying value of n. Now orthogonal property, integral minus infinity to plus infinity e raised to power minus x square hmx hnx dx equals to 2 raised to power n factorial n root pi delta mn. Here this is chronicle delta. Now recurrence formulae of hermite equation. First is 2n hn minus x is equal to h dash nx. We get this relation if we differentiate the Roderick formula of a hermite function, and this is the second relation. This relation can be get if we do partial differentiation of Roderick formula of hermite equation, and especially with respect to t, and putting n equal to 0 after partial differentiation. And in this relation we partially differentiate hermite Roderick formula with respect to x. Now another relation, hn dash x is equal to 2x hnx minus hn plus 1 x, and this is another important relation, h double dash nx is equal to 2x h dash x plus 2n hnx equals to 0. Using first and second, we get the third equation, and differentiating this third equation with respect to x, we get this equation. Now some important relations. h2n plus 1 at x is equal to 0 is equal to 0. h dash 2n at x is equal to 0 is 0. M time differentiation of hnx is equal to 2 raised to power n factorial n divided by n minus m factorial hn minus m. Here this is only for when n is greater than m. Now another important relation, this is equals to root pi into 2 raised to power n minus 1 factorial n chronicle delta m comma n minus 1 plus 2 raised to power n into n plus 1 delta n plus 1 comma m. Here h2n at x is equal to 0 equals to minus 1 raised to power n 2n factorial divided by n factorial. Here as in legendre polynomial, minus pnx pn minus x is equal to minus 1 raised to power n pnx. Here similarly in hermite function also, this is equal to this. Now another topic is Laguerre differential equation and Laguerre polynomial. Laguerre differential equation. Here this is second order differential equation, and this is equal, and x y double dash plus 1 minus x y dash plus ny equals to 0. Using Roderick power series method, we can find the solution of this differential equation. Here this is a solution. Here Laguerre polynomial is denoted by ln x, which is equal to summation n is factorial n x raised to power r divided by factorial r square into n minus r factorial. Now Laguerre function for different value of n at x equal to 0, Laguerre function become factorial n. For n equals to 0, ln 0 x is equal to 1. For n equals to 1, it's become this. For n equals to 2, this is equal to x square minus 4x plus 2, and L3x is equal to minus x cube plus 9x square minus 18x plus 6, and L4x is equals to s raised to power 4 minus 16x cube plus 72x square minus 96x plus 48. Now generating function. One minus t summation n equals to 0 to infinity ln x t raised to power n factorial n equals to e raised to power minus xt by 1 minus t. Now Roderick formula of Laguerre polynomial. Ln x is equals to e raised to power x divided by factorial n time differentiation of e raised to power minus x raised to power n. Now their recurrence relation. First recurrence relation is this: ln minus 1 x plus x minus 2n minus 1 ln x plus n square ln minus 1 x equals to 0. We can differentiate the Roderick formula. We differentiate the generating function with respect to t. We can get this relation, and similarly another relation we get by differentiating generating function with respect to x, which is equal to this. And if we differentiate this first relation with respect to x and put n equals to n plus 1, and similarly second relation, if we differentiate this with respect to x and putting n equals to n plus 1 and using both equation, we get the third relation, which is equals to this. If we differentiate generating function with respect to t by n times using Leibniz's theorem, we get another fourth important relation of Laguerre polynomial, which is this. Now, orthogonal property of Laguerre polynomial. Limits 0 to infinity, integral of e raised to power minus x lmx ln x dx is equals to chronicle delta mn. As you know, if m equals to n, then it's become 1. If not, it's equals to 0. Now, the final special function is associated Laguerre polynomial. This is a differential equation of associate Laguerre polynomial, and this is Roderick formula. Here this k is represent differentiation of Laguerre polynomial k times. Now, generating function of associate Laguerre polynomial. This is the generating function of Laguerre polynomial. Now, orthogonality of associated Laguerre polynomial. Integral limits from 0 to infinity e raised to power minus x integral of e raised to power minus x x raised to power k ln k x lm k x dx equals to n plus k factorial divided by factorial n chronicle delta mn. Now, recurrence relation of associated Laguerre polynomial. Ln k x is equals to ln minus 1 k x plus ln k minus 1, and this is second recurrence relation. Thank you.